look at worksheet 1A, which is dealing with some force diagrams. Before we get too far into this, make sure for each one of the problems you put a dotted line around your object hinges to define your system. Make sure that you state whether the acceleration is 0 or not 0, and if the net force is 0 or not 0, or state what the actual net force is. So we'll go ahead and jump into problem number 1. Taking a look at this, it says the object lies motionless. So the first thing we want to figure out is the acceleration is 0, and if the acceleration is 0 is 0. Obviously, I'm going to talk quickly through this. You can pause and rewind if you need to. Define the system in the picture. Acceleration is 0, net force is 0. So we're going to put this dot here representing the center of mass, which that dot represents the entire object. And from here, we've got a force of gravity on the object by the Earth. And we want to measure that force of gravity because the net force is 0. The net force along the y or vertical axis is going to be 0. This is on a surface, so force normal on the object by the surface. And because the net force is 0, these two forces have to be the same size. Taking a look at problem number 2. We've got the object slides at a constant speed without friction. Now that's pretty unique, kind of like an air puck in the classroom, or perhaps a puck across ice or something like that. In this case, because it's a constant speed, we know the acceleration is 0 because the velocity is not changing. Since it's not accelerating, there can be no net force. We want to start with our center of mass. And because gravity is acting on it, we're going to have force of gravity on the object by the Earth. And the same size, it's not accelerating up or down, so we're going to have the same size normal force. Now, because this is without friction, we're going to have a reason for that. Is it a puck on ice? Is it an air puck? Or is it an air hockey table? So we're going to say force normal on the object. And I'm just going to say, like we were doing with the frictionless puck earlier in the week, air. And each of those forces have to be the same size. Number 3, we've got an object slows due to friction. So there's going to be friction and it's slowing down. So the acceleration is not going to be 0, which means the net force is not going to be 0, defining the system. According to this, because these motion lines are getting closer together, we're going to assume this is moving to the right and slowing down, moving to the right, which means friction is going to be opposing that motion. So let's take a look. We've got our center of mass, and just with the other problems, we've got force of gravity on the object by the Earth, and the same size upward force. It's not accelerating up or down. Doesn't look like I drew that very well, so we're going to go ahead and have to shorten this. Go ahead and measure, and force of gravity that side. So now we got force normal on the object by the surface. And which way would be friction? If the object's moving to the right, the friction opposes that motion. So we're going to have a force of friction on the object by the surface. Please make sure that you use the lowercase f for friction because the capital F means force. Secondly, you want to make sure that the last subscript, what's causing the force, or the dealer of the force, is the same letter and same item as the normal force. Those two have to be the same. The last letter of the normal force and force of friction in this case. So the object is slowing down due to friction, in which case you could have also said that the force of friction, or the net force, the net force you could have said is equal to the force of friction on the object by the surface. Great, we're doing awesome. Let's keep cranking. Object is suspended from ceiling, so we're assuming it's just suspended. It's sitting there at rest, so the rate of acceleration is 0. The net force is 0. The center of mass, so this dot represents that object that's running there. And we've got force of gravity on the object by the Earth. And because it's not accelerating, there's no net force, so the forces along the y-axis or the vertical axis have to be the same. This is a cable or wire hanging from there. I'm going to use a wire or rope. Let's say wire. Force of tension on the object by the wire, and these two have to be the same size. I notice I'm missing my force vector there. Next one, number 5. We've got object is pulled with a rope at a constant velocity parallel to the surface, and there is friction. So the first thing we need to do is define the system. Because it's a constant velocity, That means the velocity is not changing and therefore the acceleration is 0. If it's not accelerating, then that force must be 0. We draw in our center of mass, and we've got a force of gravity on the object by the Earth. Because it's not accelerating up or down, the normal force is going to have to be the same size, force normal, on the object by the surface. The surface is applying that normal force. Those two have to be the same size. The written description said there's a force of tension on the object by a rope to the right, and then the same size force, so we'll have to put double hash marks in these, is the force of friction on the object by the surface. Just as we did on the one of the earlier problems, because there's a force of friction, that last letter by the surface has to be both for the friction and the normal force, because friction is a component of normal force. We're doing really well. Let's keep this cranking. We got problem number 6. Define the system as the object. It is pulled up at a constant speed, which means the velocity is not changing, so the acceleration is 0 and the net force is 0. Define the system with the dotted line, and we put the center of mass over here. Again, we got force of gravity on the object by the Earth, and the upward force the same size, force of tension on the object by the string or the rope. I'm going to call it a rope, and those have to be balanced. Number 7, it looks like this thing is speeding up as it's falling. The object's falling. It is accelerating, so the acceleration is not 0, and the net force will not be 0. It is accelerating. In this case, the only force acting on this is the force, that's kind of a sloppy error, the force of gravity on the object by the Earth. And that's the entire only force acting on it, which means it's also the net force. So you could have written the net force is the force of gravity on the object by the Earth. We're doing great. I was going to break this into 2 videos, but let's just get it done. This object is moving at a constant velocity, so basically it fell, and as it ran into more and more molecules of air, the drag became significant enough that we have to acknowledge it, and it has now reached some maximum speed. So the acceleration, since the velocity is constant, the velocity is no longer changing, the acceleration is 0, and that means the net force has to be 0. Center of mass representing the object, force of gravity on the object by the Earth, and then what would that upward force, if it's running into air molecules to such an extent that it's no longer allowing it to speed up, we call that drag, force of drag on the object by the air, and those two have to be the same size as each other. And number 9, the last one, the ball is rising for a parabolic trajectory, and we need to make sure that the ball on the way up is slowing down, so we know the acceleration is not 0, which means there has to be a net force, and the net force cannot be 0. We define the system as just the ball, and what forces are acting on this ball? Only the force of gravity on the ball by the Earth. And in this case, it wouldn't matter if the ball was on the way up or at the very highest point or on the way down. If you ignore air resistance on this one, the only force, and the net force in this case, is the only force of gravity on the ball by the Earth. I hope that helps. I know we went quick, but remember, you can always pause, rewind, replay as you need to. Thanks.